The second video for 7.2, we're going to look at some growth and decay. Uninhibited just means it could continue forever. Nothing is hampering that growth or decay. And so this phrase you probably have heard before in math. You've heard that word proportional or directly proportional. What that means, so if we say y is directly proportional to x, it means that y equals some constant times x, okay? And we call that k, or our constant of proportionality, that scalar multiplication that we're using. So we have many situations where we have a certain quantity. We're going to use A for amount. This could be amount of people, amount of money, amount of bacteria, whatever we're looking at, that varies with respect to time in such a way that our rate of change, remember anytime we hear that, that means derivative. So our rate of change for A with respect to t would be our dA dt, and it's proportional to our original amount itself. These situations can be modeled by differential equations. So let's go ahead and write, so if it is directly proportional like it says, this is the differential equation that kind of models this situation. So we're going to solve it for our general solution here, you guys. So we have this this differential equation. I'm going to move my a's to be with dA, and I'll move my dt to the other side. So I'm going to get 1 over a dA equals k dt. We're going to integrate both sides. So I have the natural log of a equals k times t plus our constant. Now, if a is greater than 0, which if we're talking about amount of people, amount of money, amount of bacteria, this typically is positive. So we're going to use natural log of a equals kt plus c, so long as a is positive, right? Okay, and for most of our situations we're going to be dealing with, we don't have to worry about that. So the other thing to note is that we will use a equals a naught. This notation, this a naught, is the initial amount. So when our time starts, we're going to say time is 0. This is an initial given condition. Okay, so if I were to plug in a naught for a and 0 for t here, we would get the natural log of a naught is equal to our constant. Okay, so in doing that, kind of bring this up here again. So we're going to have natural log of a, so I'm rewriting this equation right here, equals k times t, but we're going to plug this in for c, plus natural log of a naught. And again, a naught is our initial amount when time is 0. Okay, so now I'm going to just do a little rearranging. I'm going to subtract my natural log of a naught. So in getting my natural logs on the same side, I can use my condensing rule that subtraction condenses to division. And then I can exponentiate both sides. I'm going to solve for a because a is that amount that we're solving for after a time t typically. So I'm going to exponentiate both sides. So I have canceled over here. So we have a over a naught equals e to the kt. Multiply both sides by a naught, and we get this equation. This should hopefully look familiar to you. You might have seen it in this format a decent amount. PERT, right? This is an exponential equation for growth or decay. So an exponential equation is a solution to this differential equation. So if we have this differential equation, we did the long step of separating the variables, integrating both sides, rearranging algebraically. But if you see this, you guys actually automatically know now that this is our solution. So we can use that to solve some problems. And then a naught, again, you guys, is the initial amount. Okay, so let's do a problem. Okay, so if we have a situation where we have something growing or decaying, kind of there's two things we can recognize. These exponential growth and decay problems, you guys have done a lot of these in your math career, Algebra 2 and Pre-Calc included. So there's a couple ways we can recognize them. We might just recognize the phrasing of the exponential growth or decay. In calculus, you might see this phrase a decent amount. This part. Bacteria grows at a rate proportional to the number of bacteria present. So rate, remember, is derivative. So they are saying, again, I'm going to use A, so the amount of bacteria with respect to time, that rate, which is this, is proportional to the number of bacteria present. So K times A. K is that constant proportionality. This has that form that we just looked at. So my solution then is A equals A naught e to the KT. All right, in all of these, just so you guys are aware, you are going to have to solve for K first, okay? So let's plug in what we know, and we are going to solve for K. So I'm going to just write that in. We'll always solve for K first. Okay, so here is what I have. We have the population of this bacteria colony doubles in 5 hours. So we have some initial amount, we're not sure how much, right? We don't know our K right now, but after 5 hours, this population doubles. So it got multiplied by 2, right? We're going to solve this for K. So I can divide out those A naughts. And now I want to solve for K, so I can take the natural log of both sides, which will cancel out my E. Natural log of 2 over 5 then is our K. Go ahead and leave it in this form. Don't worry about changing it to a decimal. It'll be more accurate for our final answer. So now they want us to look for how long does it take for the population to triple. So now we're solving for T, right? We want how long. So we want our amount to triple. So again, I don't know the initial amount, but if I'm tripling it, whatever the initial amount is got multiplied by 3. And again, we now know K is natural log of 2 over 5. And then we are solving this for T. Again, I can divide out the A naughts. So I have 3 equals E to the natural log of 2 over 5. Natural log both sides. I'm going to multiply by 5 and then divide by natural log of 2. So we have 5 times the natural log of 3 divided by the natural log of 2 is our time. And then I can enter that in. So we've got 5 times the natural log of 3 divided by natural log of 2. So we get T is approximately 7.925. And again, with these ones, we want to put years on it, or sorry, units. In this case, it's going to be years, hours, not years, sorry. Because they're asking about how long. So what was our time unit? It was hours. And they might ask us to round to the nearest whole number or things like that, but 3 decimal places otherwise. Okay, another very common exponential decay problem is anything involving half-life. Those should sound familiar to you as well. So this is a half-life question. I automatically know I'm going to use this formula. Okay, and we know at this stage we're going to have to find K first. So let's see what we have. We have a half-life of carbon-14 is 5,730 years, okay? So we're trying to find out how old this animal skull is, but we are going to know that half of our amount right? If my original amount is A naught, half of it's going to be left after 5,730 years, right? So this is going to allow me to solve for K. Again, I can divide out the A naughts. Take the natural log of both sides. So natural log of 1/2 divided by 5,730 is our K. That is how fast this thing is decaying, is growing. That's our rate. Okay, now to go back to the question, again, we're asking how long, so we're solving for a t. How long ago did this animal die if they found a skull that's now containing 20% of its original amount? So 20%, I can write as 0.20 of its original amount. We don't know the amount, but we can just write it as A naught. We now know K. Natural log 1/2 over 5,730, and then we are solving this for t. Again, the A naughts go away. We're going to natural log both sides. Okay, so we're going to get 5,730 times natural log of, natural log of 0.2 over natural log of 1/2 equals t. All right. Again, some calculator work. So we've got 5730 times natural log of 0.2 divided by natural log of 0.5. Okay, so we get our time is approximately 13,304.648. And our time unit in this case is years. So that is approximately how long ago this animal died. Okay, another common problem, you guys, for exponential growth or decay is Newton's law of cooling. You might have seen this before, if not in a math class, perhaps in like a physics or chemistry class. And so we're going to use U of t to represent the temperature of a specific object at time t. This capital T is going to represent a constant temperature, so like the surrounding temperature of a room, for example. So I'm going to kind of do this the long way again, you guys, just to show you where the solution comes from, and then we can use that solution format from here on out. So here's our equation. I'm going to go ahead and get this over with du and this with dt. So if I separate that, I'm going to get 1 over u of t minus t du equals k dt. So that's just separating. I divided this piece over to the other side. Now, our surrounding temperature for this particular situation, so we have an object that's 90 degrees Celsius, is cooling in a room that has a constant temperature of 20. And then we're also told after 10 minutes, the temperature of the object is 60. What will the temperature be after 20 minutes? So our constant surrounding temperature is 20. I'm actually going to go ahead and put that in there. Okay, so if I integrate both sides, we have natural log of u of t minus 20 equals kt plus c. All right, so let's go ahead and put in our initial temperature. So at, we're going to say u of 0 is 90, right? So before time starts, this object is 90 degrees Celsius. So I can go ahead and put in 90 and 0 for t to solve for c. Okay, so let's see, we get natural log of 70, which is positive, equals RC. Okay, so back to my, so this was my general, then my specific solution is going to be natural log of u of t minus 20 equals kt plus my c value, natural log of 70. Okay, so this is my particular solution for this situation. Again, I'm going to rearrange this a little bit, you guys, because you will see Newton's solutions kind of in a different form, where we're solving for u of t. So I'm going to go ahead and move my natural log to the same side so I can again condense them. So I've got, if I subtract that to the other side, I can condense the subtraction through division. Okay, so we've got u of t minus 20 over 70 equals kt. Okay, I'm going to exponentiate both sides. So we have u of t minus 20 over 70 equals e to the kt. Multiply by 20, or by 70, excuse me. Sorry, it got a little blurry. Multiply by 70. and then we add the 20. Okay, so this is kind of, so this is our particular solution rearranged, but this is kind of something to know. All Newton's cooling problems will have solutions of this form. And kind of some things to know. This is the surrounding temp, which we knew that. And then the 70 is the difference in the object and the surrounding temp. In object, temp, and surrounding temp. Okay, so now let's use that specific solution to answer our question. Again, to start, we do have to find K, always. All right, so they give us another time scenario. After 10 minutes, the object is 60. So 60 is our temperature after 10 minutes, so we're going to plug in 10 for T. So I had 70 e to the K. We're plugging in 10 for T. Okay, so we are solving this for K. Subtract 20 and divide by 70. Take the natural log of both sides, and I'm going to reduce this to just 4/7. So natural log of 4/7 over 10 is our K. All right, so now our question, what will the temperature be after 20 minutes? So we are solving for U of 20. All right, so we have 70 e to the, we now know K, natural log of 4/7 over 10 for 20 minutes. So we're going to plug in 20 for T and then plus 20. Again, this is all just some calculator work to find U of 20. So we've got 70 times e to the natural log of 4/7 divided by 10, and then times 20 plus 20. All right, so we get 42, and this is a temperature of the object after 20 minutes. So it's approximately 42.857 degrees Celsius. All right, guys, that's it for the second 7.2 video. Thanks for watching.